Hello everyone. I welcome you all for today's session on machine learning with Python. Introduction Module 1. We'll be concentrating today on version space and list then eliminate algorithm in detail. I am your friend Mahadev, Assistant Professor, Department of ENC, Gaussian College of Engineering. If you like my videos, subscribe to my channel, click on the bell icon for further notification. Or if you like the videos, share with your friends for the benefits. First, as I said, we'll be concentrating today on the topic called as version space. Version space. The key idea in the candidate elimination algorithm is to output a description of the set of all the hypotheses consistent with the training example. If you take any training example of a particular problem, we have a set of hypotheses present in that. We have to find the consistency present inside the hypothesis for the correct result there. So how we are writing that? Let's see the representation there. So definition of that one, what we can say is that consistent. A hypothesis H is consistent with the set of training example D if find only if H of X is equal to Cx for every example X comma Cx in D. As we can see the definition, we can say it has consistent, the hypothesis as a consistent in the training example T there. Whatever the hypotheses which are consistent, it has to satisfy certain condition there available in the training example for every instance of X. The condition is H of X should be equal to C of X. So this is the condition for satisfying the consistent there. The difference of consistent and the satisfy is that, let's see, an example X is said to satisfy hypothesis H if there is one H of X is equal to 1, regardless of whether X is positive or negative example of the target concept. As we have seen in finder's algorithm, we have considered only the positive examples. Now, if you see it in version space, we are concentrating on even the negative examples as well as positive examples there. And the condition is what? If it is satisfying means H of X is equal to 1 there. Consistent means here H of X should be equal to the target function, that is C of X there. And if this is the difference, H of X is equal to 1 for satisfying the condition, whereas H of X is equal to the target function C of X there. So let us understand that what is the version space there. As we already seen the definition here, version space, the version space is denoted by VS H suffix D there. That is version space hypothesis for the examples, what we have trained example there. With respect to the hypothesis space H and training example D is the subset of hypothesis H, that is hypothesis from H consistent with the training example here. So version space, what we are saying VSHD here is equivalent to the hypothesis belongs to the H, that is the overall hypothesis present inside that. If it is satisfying the consistent property, so what is it consistent means H of X is equal to C of X. If this condition is satisfied, then we can include that in a version space H there. Now let us see a simple analysis what we have with the help of list then eliminate algorithm. So list then eliminate algorithm first initialize the version space to contain all the hypotheses in H and then eliminate any hypothesis found inconsistent with any training example. So the concept what it is saying that whatever the training hypothesis we have got it with the trained example, all should be brought into a version space there. And in that, we have to find the hypotheses which are consistent. And if it is not consistent, we have to eliminate that. That's why we say listing all the hypotheses and eliminating which are not consistent. In simple way to make you understand about list then eliminate algorithm. First step is what we have is in version space, a list containing every hypothesis in H, as we already shown in the previous figure. So this capital H consists of the 5 hypotheses what we analyzed it for any particular example. And for each training example here, instant X of a target function C of X, we have to remove from the version space which are not satisfying the consistency property there. So as we said, consistency is what? H of X is equal to C of X. And if it is not satisfying, we have to remove it. So finally, after removing whatever the hypothesis is being left, they are all called as output the list of hypotheses in version space, inspecting all the training example. So this is the simple algorithm for the list then eliminate algorithm. In detail, let us see it. So what we have to do in the list then eliminate algorithm is that we have to list all the hypotheses into the version space as the definition says. And then we have to see which are all the satisfying the consistency property that is h of x is equal to c of x. Now let us assume that we have h1 and h2 are consistent with each x1, x2 and x3. And whereas H3, H4, H5 are not consistent. That means in version space, it has only H1 and H2. Why? It satisfies the each and every instance of X1, X2, X3 of the trained example, which is satisfying the consistency property. So whatever the hypothesis is present overall, only two are being considered, that is H1 and H2, which are satisfying all the instances there. So this is how what we are doing. We are allocating all the hypotheses for the version space. In that we are selecting only in this particular example two hypotheses h1 and h2 because it satisfies all the instance present in the trained example x1 x2 x3. It means it is satisfying h1 of x is equal to c of x1, h1 of x2 is equal to c of x2, like that it is satisfying all the instance present there. So list then eliminate works in a simple principle so long as version space is a finite. So one restriction what we have is that the version space, it belongs to a finite hypothesis what we have there. So however, since it requires exhaustive enumeration of all hypotheses in practice, it is not possible here, feasible. So a more compact representation for version space is required, because we have to check each and every hypothesis present inside that. So the version space is represented by its most general and the least general members. As well as seen the version space, it consists of all the possible configuration varying from the general to the more specific and the most general members there. And these members from general and the specific boundary sets will delimit the version space within the partially ordered hypothesis space. Now, due to this restriction problem, it is being delimited in the version space because of the partially ordered hypothesis present inside the version space there. So what the theorem says here is that version space representation theorem. So version space representation theorem we can see here. Let X be an arbitrary value set of instance and let H be the set of Boolean valued hypothesis defined over X. Let C be the function of X, that is 0 to 1 Boolean function, an arbitrary target concept defined over X, and let D be the arbitrary set of trained example. So whatever the instance X is there for the trained example present inside that, for all X, H, C, and D, such that specific and the general are well defined here. So if you observe, this is a theorem definition what we have. Version space for the hypothesis of a trained example. V stands for version space, hypothesis for a trained example. For whatever the hypothesis which is present inside the overall hypothesis, for every specific case of algorithm or the general case G, the condition is that it must satisfies in between the general and the most specific one here. Okay, this is the theorem which has to be defined or proved there. What we have to prove here, every H satisfies the right hand side of the above expression in the VSHD. Whatever the VSHD expression is here, it must satisfy the right hand expression. And every member of VSHD satisfies the right hand side of the expression is very, very important there. So how to prove it? Now let us sketch the proof for that particular thing. So let G, H, S be an arbitrary member of specific hypothesis and a general hypothesis and specific respectively, with condition that general is greater than or equal to the hypothesis whatever we have, considering over the more specific there. So by the definition of specific, S must be satisfied by all the positive examples in D. Because since it is specific, it must satisfy all the positive examples in the D, because H is greater than S. So H must also satisfied by all the positive examples in the D there. By the definition again here, G cannot be satisfied by any negative example in T there because G is greater than H. As we can see, G is greater than H cannot be satisfied in any negative example. So condition is what? So G cannot be satisfied for the negative example. If it is not satisfying, it cannot be eliminated there because H is satisfied by all the positive examples in D and by no negative examples in D. So H is consistent with D. So with the definition of this one conditions, H is always consistent with the trained example present in there. Therefore, H is the member of version space HD there. So it can be proven by assuming that H is in VSHD that does not satisfy the right hand side of the expression, then showing that this lead to an inconsistency. So if it is not satisfying, we can easily say that H is inconsistent in nature if it is not satisfying the above theorem property there. Okay. So this is how the list then elimination algorithm works there. So we have to list all the hypotheses present inside the trained example into the version space, and in that whichever is not satisfying has to be eliminated and whichever is satisfying has to be kept. So that's why we call this algorithm as list then elimination algorithm. So if you have any questions, go to the comment section, write down your questions. I'll reply to your questions. If you like my video, subscribe to my channel, click on the bell icon for further notification or share with your friends for their benefits. Thank you.